Okay, welcome back. The last talk of today before the exercises will be by Anton Dzhamay. Correct?
Yeah.
Oh, I learned how to pronounce your name. And the title is Geometry and Symmetry of Painlevé equations.
Okay, well, thank you very much. And thank you for still being here. So I realize that everybody are getting tired. So I decided that my talk will be very, very elementary. And in that sense, it's not aimed at the people in the front row, but rather to the thinning back rows. Okay? No, we don't have time. Right? No offense was intended. Okay, so, but again, I'll try, rather than focusing on actual equations and formulas, I'll try to explain a little bit of the general picture of the theory of Painlevé equations from the geometric point of view. Okay? So that's essentially the title of my talk, Painlevé equations, geometry, and symmetry. And the plan of the talk is the following. So first, I will say a few words about Painlevé equations. Like, what are they? And why are people interested in them? Second, I will explain where the geometry appears in the theory of Painlevé equations. And this geometry is known as Okamoto space of initial conditions. Okay? Which, despite the way it sounds, is actually a family of certain rational surfaces, rational algebraic surfaces, so-called generalized affine surfaces. Okay, so we start with some equation. From that equation, we can get a geometric object. And then we can look at the symmetries of this geometric object. And so symmetry comes from geometry. And symmetry here are something called Cremona isometries. So these Cremona isometries are associated with the surfaces here, and the group structure of Cremona isometries in this case would be some Weyl group associated to some root system or some Dynkin diagram, and this Weyl group would be affine and also extended. Okay? And the nice thing about this is by looking at geometry, it's clear how to compute these symmetries. And what the symmetries do, they create symmetries of your equations. They are known as Backlünd transformations. So Backlünd transformations, these are symmetries of your equations. Okay? And because we have an affine Weyl group, so this is like step 3, and I think I'm done with my title, and I'm very afraid that that's about where I would start running out of time. However, if there is a little bit of time left, because Weyl groups are affine, from here you have translations. Translations in affine Weyl groups. And you can think about such translations as defining a discrete dynamical system. You just go by some fixed vector in some affine space, and associated to this fixed vector is actually a nonlinear equation, and this nonlinear equation became known as discrete Painlevé equation. And the reason such equations are known as discrete Painlevé equations is because you can do a continuous limit, go full circle, and get back to a Painlevé equation. But what usually happens is you start with some Painlevé equation, for example, Painlevé-VI, find its associated geometric object, look at its symmetries. In Painlevé-VI, it will be affine D4. Look at translations and take continuous limit, you will end up with a Painlevé-V equation. So this would be like a discrete Painlevé-V. Okay? So my goal is to give you some idea of how this machinery works. Yes, there is something called Q Painlevé-VI. And that's not something that I will be talking about. Okay? I apologize if I'll be shutting questions down a little bit because there's a lot of stuff here. You open the lid a little bit and there's a whole Pandora box of interesting stuff. If you want to sacrifice a coffee break, let me know and then. Huh? Affine D4. I don't understand. Huh? Yeah, you'll see what it means. Okay, so as I said, my talk is for the tired people at the back, essentially. That's why, to explain what a Painlevé equation is, I will start with something very simple, like y prime is equal to y, and I apologize for doing that. Now, why is this equation important? Because this is an example where you start with an ordinary differential equation, and you get an interesting or special function as a solution. In this particular case, of course, the function that you get is one of, if not the most important functions, right, the exponential function. And the way to think about that is you allow t actually to be a complex variable. You allow complex time. And then you can think about this as a power series. And that follows directly from your differential equation using the method of Frobenius. And all the properties of the exponential function, like the fact that it takes addition into multiplication, you can get directly using the language of differential equations. Okay? So ordinary differential equations is a good source of interesting new functions. Of course, this is something very, very simple. If you try to do something a little bit more interesting, you can try, and I know I should remember this, but I don't. You can look at the following equation, E of alpha, beta, gamma. Okay? So and this equation is known as a Gauss hypergeometric equation. Huh? Can I read it? Yeah. E alpha, beta, gamma. So it's a second derivative of some function w with respect to time, and coefficient gamma minus alpha plus beta plus 1 multiplied by t divided by t1 minus t dw dt, and then minus alpha beta t1 minus tw equal to 0. So this is known as a Gauss hypergeometric equation. And this is one of the sort of prototypical examples of differential equations that gives a source to many special functions through degenerations. If you think about time t, actually not even a complex parameter, but living on the Riemann sphere, this is an equation that has three singular points, or three regular singular points, one at 0, the other one at 1, and the other at infinity. Okay? And the reason you have singular points is because you have singularities in the coefficient. When t is 0 or 1, this coefficient is equal to, the denominator here becomes 0, or if you clear it off, the coefficient at the highest derivative disappears. So you see that we have singularities. Okay, and the singularities can occur in two different places. You can think about singularities occurring. Oh, nice. You can have singularities occurring in equations, and you can have singularities occurring for functions. Okay, so equation or solution. Okay. And then the question is, how are the two connected? If you have a singularity of an equation and a singularity of the solution, well, it turns out that you can sort of say something like this for linear ordinary differential equations. So what I'm saying is the following, that if your equation has coefficients that stop being analytic, for example, at a certain point, you can have solutions that become singular at that point, but not necessarily. You may have solutions that are not singular. For example, for the Gauss hypergeometric equation, you have something called the Riemann scheme. And these parameters, alpha, beta, and gamma, that we saw there, I think, no. Okay, tell you that you have a fundamental system of solutions, one of which is regular, and the other may have power behavior of 2 minus gamma at this singular point and behavior at infinity. So here you have your alpha, beta, and gamma as complex parameters. So in the linear case, the control over singularities of solutions is completely provided by the equation. However, if you go from linear equations to nonlinear equations, a whole lot of properties disappear and life becomes very different. On the other hand, if you are using differential equations to describe special functions, it makes sense to try to construct nonlinear special functions from nonlinear differential equations. Okay? But then there is a problem. And so let's take equation that is as simple as the very first one that I wrote. So dw dt, but instead of y or w, I'll take w squared. Okay? This is a simple first order separable equation, for example. You solve it by rewriting in differential form and integrating. Okay? And how do you find this constant of integration? Well, you need to have an initial condition provided. So let me add to my equation an initial value problem that w at t naught is w naught. Then it's easy to evaluate this. This can be written as t minus t naught minus 1 over w naught. And then you can solve for w of t. This would be something like w naught 1 minus w naught t minus t naught, or something like this. Okay? Up to small typos. So what do you see? First of all, you see that this solution has a pole, because denominator can vanish. Second, you see that the location of a pole, so this is a pole, at time t, and you can see it from here. So what is my t is 1 over w naught plus t naught, I think, something like this. Okay? So such singularities are called movable. So this is a movable singularity. So movable singular point. And the word movable here means that it depends on initial conditions. Okay? So now, it's not the equation that controls your singularity structure. It's the initial value problem that controls the singularity structure. And a pole is something that we can handle. But if you look at something like this, w squared dw dt, let's say 3, is equal to 1, and let's say w of 0 is w naught, because of course the initial value of time doesn't matter. Here you will get something like w cube is t plus w naught cube, and you solve. You get the branching point phenomena. So now you have a singular point at minus w naught cube, and then another singular point at infinity, and you need to do a branch cut. And here, the location of the branch cut starts depending on initial value problem. And that really is an issue, because if you want to construct the Riemann surface of this solution, you really need to introduce moduli on these Riemann surfaces. So, and what that means is what we have here is actually still good, but what we have here is really not good. Okay, and this is not a very mathematical way to say it, but a mathematical way to say it is that here you have Painlevé property, and here you don't. Okay, so Painlevé property is, of course, goes back to Paul Painlevé. And he was interested in finding differential equations and classifying differential equations whose general solution has no movable points like branch points. For simplicity, we can say that Painlevé property is general solution or movable singularities of general solution are poles. Okay? So that's Painlevé property. And Painlevé, together with his students, but especially Gambier. No. Painlevé property is general. I think I'm thinking in terms of. Okay, let me think about it. You caught me off guard a little. Definitely for second order, yeah. Okay, yeah, we'll talk. I always work in second order, so I don't think beyond. But I think it's the same for third order equations and higher order equations. The Painlevé property is still the same. Okay. Oh. Anyway, so there is a classification due to Painlevé and Gambier, and then independently Fuchs, of special second order equations that satisfy this property. So equations are of the form like this, and here you have some rational expression in W and T. So you have P1, and I apologize, I have horrible memory, so I cannot remember equations at all, even as basic as Painlevé-I. This is embarrassing, but it is what it is. So you have Painlevé-I, have Painlevé-II, d2w dt square is and what's interesting here, you see that there is a parameter alpha appearing, and you have Painlevé-III, and I don't want to write it. And then you have Painlevé-IV, and that one I will write. It's a bit more complicated. Okay, and again, you see here that you have parameters now alpha and beta appearing. Okay, and there are two more. There is Painlevé-V and Painlevé-VI, and if people are feeling that they should add two more to Painlevé-V, don't. I know about them. Okay, these equations, they come in a cascade, so you have more parameters in Painlevé-VI. You try to degenerate parameters. You can degenerate to Painlevé-V, and you can degenerate to Painlevé-IV and Painlevé-III. You can in turn degenerate this to Painlevé-II, and all the way to Painlevé-I. So that's one thing. And another thing is you have special values of parameters alpha and beta that give you special solutions. Okay? So for example, here you can get this hypergeometric functions as a solution of Painlevé-VI, or solutions of Painlevé-VI expressible in terms of hypergeometric functions for certain values of parameters. Yeah.
Why this study all six? Because it seems like every generation of number six.
Well, you have different properties. You have different symmetries. You have different type of special solutions. So it's not that if you know, well, first of all, I think it's hard to know everything here. It's much easier to know more here than there, right? So you have that. And if I can get a bottle of water that I didn't think about, I would appreciate it. No. Okay. So we have special solutions. So here, so here we have Kummer, here we have Bessel, yeah, here we have Bessel, here we have Airy, etc., Hermite. Again, it's important that there's some values of parameters that are special. Okay. But in general, it is very difficult to keep any track of solutions of Painlevé equations. The method of Frobenius doesn't work. How do you represent a solution? How do you study its properties? And there are a large number of techniques. For example, you can use something known as a Riemann-Hilbert analysis. But one of the approaches on trying to describe solutions is due to K.Okamoto. And now I am moving to the second part of my talk. Who decided to understand the solutions or parameterize the solutions by initial conditions, which is the most natural thing, right? Try to, by Cauchy theorem, your initial condition uniquely determines your solution in some time interval. But for that, it's better. So for example, if you start with P4, it's better to rewrite that as a Hamiltonian system, H4. And there's a little bit of a catch here. So Okamoto Hamiltonian for H4, and I will use here variables f, g, and t. That would be 2f g square minus f square plus tf plus kappa naught g plus theta infinity f. Okay? Now, here, notice that even though I call this function as Hamiltonian, it is something known as a time-dependent Hamiltonian function, so it is not a constant of motion. It's evolving with time, but nevertheless, you can still take the symplectic form, and let's take the standard symplectic form dg df, and generate your equation, then you have f dot is hg, and g dot is minus hf, and okay, I should be able to do that. 4fg, right, minus f square plus, I'm just following the advice of Ned to do it in public, right? So here, what do we have? Minus 2g square plus 2fg plus tg minus theta infinity, something like this. So you get a Hamiltonian system, but notice that it's not that f a coordinate and g is a momentum. It's a little bit more complicated than that. Okay? And turns out that this system, if you rewrite it for just f of t, let me call this Painlevé-IV denoted by star. So here, this is star for w of t is f of t. And notice that here I used parameters alpha and beta, and these are standard parameters for this standard form of Painlevé-IV. And here I used kappa naught and theta infinity. And they're related, of course. So alpha is 1 plus 2 theta infinity minus kappa naught, and beta is minus kappa naught square. But of course, I could have skipped that. But the reason I'm showing this is when you have equations coming from a particular applied problem, your parameters are related to parameters of a problem, and you need to be able to match them with the standard parameters. Sometimes it can be difficult, and geometry actually tells you how to do that. But, okay, anyway, so you can show that this system is equivalent to Painlevé-IV. Then you start thinking about the space of initial conditions. Everything is complex, so this line is actually a complex plane in the colloquial sense. This plane is an actual complex plane, C2. This is a plane of my variables f and g. And then if I pick up a point here, I will have a solution. Okay? And remember the type of singularities we're allowing for Painlevé equations. We're allowing poles. So what can happen is this equation can go away to, this solution can go away to infinity at some value of time. But on the other hand, of course, some other solution can go away to infinity for our value of time. So we want to try to account for these infinities. And what we need to do, we need to projectivize this C2. And there are two ways to do it. You can projectivize C2 to P2, or you can think about C2 as C1 cross C1 and projectivize it to P1 cross P1. And this is what I would usually do. It almost doesn't matter. For Painlevé-I, you need to do this, but Painlevé-I is also not the one I'm interested in. So if you know a little bit of algebraic geometry, you know that these two are different, but they are what is called birationally equivalent. Okay? And it's a very nice thing that now we got us a compact complex surface, two-dimensional complex manifold, or two-dimensional complex algebraic variety, and compact. So you immediately can talk about things like homology, cohomology, Poincare duality, etc. So in this case, if you look at H2 of P1 cross P1 Z, it's the same by Poincare duality as this. Is the same as H1 with the coefficient and the structure shift, so the classifying space is for line bundles. And that's the same as a peak that we saw in Sam's lectures, although in his case it was one-dimensional and here it's two-dimensional, but it's still divisor, it's a set of divisor classes, all irreducible codimension one submanifolds, which is really curves on P1 cross P1 modular linear equivalence. It's very easy to understand what this thing is. It is generated by coordinate classes H F and H, G, and I want to show it in two different ways. So what is P1? P1 is the same as a sphere, right? So if you want to think about P1 cross P1 topologically, what do you have? Really, you have a product of two spheres. It's very similar to a torus being a product of two circles, and each circle is its generator in homology. So the same thing happens here. One of the spheres is a generator, and that's exactly one of these two coordinate classes. Okay? So, and I need a way to visualize it because I like drawing pictures. So this is how I will visualize it. I will draw it as f equals to 0 line here. So this is my sort of coordinate f. And I add here the point at infinity. So you really should think about it as a Riemann sphere with 0 in the south pole and infinity in the north pole. Okay, and same here. You have g equals to 0. You have g equals to infinity here. Then you have various coordinate charts. For example, here is your little f, little g chart. And for example, over here, there is what I will introduce as a big F, which is 1 over little f, and big G, which is 1 over little g. Okay, so and then there are two more charts, one centered here and one centered here. So we have these four charts. We have this group. This group comes equipped with something called the intersection product. So H f dot hf is hg dot hg is 0, and hf dot hg is 1. And if you use this picture, it's sort of easy to see what's happening. You have a vertical line. This is, for example, f equals to a. You have a horizontal line. This is g equals to b. They intersect at one point, and that's that. Okay? Of course, these are classes, but a class of horizontal lines you just allow to deform this. And of course, if you deform here, there's still one intersection point. On the other hand, if you want to do this, you take two representatives, and you should use a general position transversality. So you take two representatives where one is a shift of the other, and they do not intersect. Actually, the right way to think about this is you do this shift by pushing the zero section along the normal bundle of the embedding of this line on the projective plane, and you can do that in this case. Okay, so we have that, and then remember our symplectic form. Of course, it's a complex symplectic form, omega dg wedge df, that is completely regular over here, but if you extend it to the all of P1 cross P1, it starts picking up poles. So omega is dg wedge df in this chart, but it becomes d capital G wedge d capital F over F squared G squared in the other chart. So you have poles of order 2. Then what this means is if you take a divisor of omega and take its class, you have poles of order 2 in the first coordinate line and poles of order 2 in the second coordinate line. And of course, this is known as the canonical class. Okay? And in Painlevé theory, this class, or rather its dual, plays an absolutely crucial role. So I'll go from here to negative k, which will be, in my case, 2hf plus 2hg. Okay? So this is how geometry appears. However, I am not done, because you can have more than one solution going to infinity. So what can happen is, where was that? Over here, right? You have one solution going to infinity here, and you can have another solution going to infinity here. This is, of course, a lousy picture, because the dimensions of what we're doing is much higher, but still. So if you think about these two solutions sort of going to infinity together, if you think about this as infinity, you have something like one solution arrives and then the other solution arrives, but they sort of have the different rate of growth. Okay? So what you can do is you can separate these solutions according to their rate of growth, or sort of naively on the slope on which they enter this point. So you have something like this. So what you do is you take this point and you do the blow up. Okay? So what the blow up does, it introduces an additional direction of slopes. So this would be your slopes. And you lift your curves according to the slope by separating them so that they don't intersect anymore. This is a very standard procedure of resolving singularities in algebraic geometry. So this is blow up at the point P, for example. Okay? So you have this line of slopes, and you can think about it in the following ways. Here, you introduce this additional line, and all possible slopes up to equivalence, that's exactly the projective line, right? So it's a space of lines, equivalence classes of lines for the point. So it's P1, and P1 was S2. So every time you do the blow up, you have to add what is called as exceptional divisor E, okay, that corresponds to this line of slopes, EI, and that will be like an extra sphere because it's your complex P1, and in your peak gets another class epsilon I. That's the class of this sphere EI. And so it's a kind of a surgery where you take a point and you take away a point and you blow a bubble at this point, or you do the sum of P1, I think, with the opposite orientation, maybe not. Okay, anyway, so you have this, and when you do this to your Picard, this EI has this interesting property that it's what is called a -1 curve. So it's a curve of self-intersection -1, and sort of the way to see it is if you think about this picture, it's of course it's a real picture trying to convey some complex geometry, but if you think about this, this is like a Möbius line bundle. So this bundle has no sections, okay? And you can think about this self-intersection as an intersection of a zero section with its deformation, and this one has no deformations. They go to infinity. So that's essentially the first Chorn class of the embedding of a normal bundle of the embedding of E in X, the surface that you get as you blow up. Okay? So you have to adjust your geometry. It's not just projectivizing, it's also separating these possible trajectories that go this way. Okay? So okay. So here is the picture then. We start with C2. We add lines at infinity. Then we look at points where new trajectories can intersect. And if you think about Painlevé-IV, that was just here, sorry, turns out that this is what you get. You get a point here and another point here. You get a point here and another point here. And you get 1, 2, 3, 4 points here. Okay? So what does this mean? It means that here you had this bad point. You did the surgery. You created a bubble at this point. You extend your equation to that bubble, pick up another bad point, and have to do that again and blow another bubble there. So this is the cascade of infinitely close points. Or you can think about sort of curves touching each other, and you need to go further. So you get something like this. So you get points P1, P2, P3, P4, P5, P6, P7, and P8. So here, these are my lines f equals to 0, f equals to infinity, g equals to 0, infinity, g equals to 0. And actually what I'm doing a little bit of a gauge transformation that I can always arrange for the points to be there. That's sort of what also normalizes the way your system looks like. But then if you think about the point P4, first we need to introduce a coordinates describing it. And to do that, so local coordinates around this point is little f and big G, where big G is 1 over G, little g. So you can introduce the coordinate like little u3, which is just f, and for big G, you write it as little u3, little v3, and this v3 is, of course, just a slope g over f. So that's a slope coordinate. By introducing this line of slopes, you just do this algebraic change of variables, introduce the slope coordinate. You can also call this a coordinate, usually called big V3, and this is big U3, big V3. And these are the two charts. One chart is sort of at the bottom of a P1 and the other at the top of P1. And you can use usually either of these charts to specify. So here, little u3 is kappa naught, and big v3 is equal to 0. That's what this point turns out to be if you do the computation. So what I want to stress is that the coordinates of these points, they depend on the parameters of your equation, on the parameters alpha beta or on kappa naught, whatever. Okay, so then what you do is you do the blow-ups at these points, and you keep track of the intersection index of your curve. So let me start with the point P1. So I have this line, and this is a 0 line, and I have this line, this is a 0 line. These are lines of self-intersection 0. I blow up this point, so it now becomes a line. Okay? Let me call this line E1, because that's sort of the sphere or the line of slopes that I created at the point P1. It has the index of -1. Then this line also becomes my index -1, and I will call it Hg minus E1, because when you project, this whole thing projects to this line. Just that the preimage of this point is this whole line. So if you want to sort of take what is known as a proper transform, in other words, preimage of this line without the point in algebraic closure, that's the notation that you would use. And here you will have hf minus E1. So that's blowing up that point in the corner. Now, there is one more point appearing. So somewhere here will be a point P2. So if we blow it up, we will create here a line E2, sorry. And this line, now by the same token, I want to write it as E1 minus E2, but I will also change the color here. Write it as E1 minus E2, because this now is a -2 curve. Okay? You can check it just by computing the intersection index. So you do it over there as well. So here you will have E5 minus E6. This line would actually be HF minus E1 minus E5, E6 minus E7, E7 minus E8, and here you will have E8. Here you will have HG minus E3 E3 minus E5, E3 minus E4. This one would be HF minus E3, and here you will have E4. You get a diagram like this, where I color-coded red curves are -1 curves, and blue curves are -2 curves. Okay? And that's where this Dynkin, that's where the affine Dynkin diagrams start showing up. Let's look at the configuration of these blue curves. If you draw them, you see that you have a chain. Let's start here. You have this curve, then this curve, then this curve, then this curve, then this curve. So this would be, let me call them D1, D2, D3, D4, D5. So this is my D1, D2, D3, D4, D5, and I will call this D6, and I will call this D0. And, oh wait, D3, D4. No, D6, D0. I'll leave it like this. Doesn't matter. Okay? So if you look at this diagram, many of you will recognize that this is what is known as a affine Dynkin diagram A6. Okay? And this affine Dynkin diagram comes with a generalized Cartan matrix. And the generalized Cartan matrix here, it's up to a sign, because we're thinking about self-intersection. So this is index -2, and then D0 doesn't intersect with 1, 2, 3, 4, 5, intersects with 6. Then D1 doesn't intersect with D0, intersects with itself, and so on. You can fill in this diagram. And this matrix is degenerate. It has a null vector or vacuum vector. That's exactly where the affine part of the affine Dynkin diagram comes from. And if you, so there is a vector here that you multiply to get 0. Turns out that you can see the coordinates of this vector from the diagram quite easily. There will be something like this. And that whole thing, if I call it delta, turns out that this is exactly the anti-canonical divisor class. And what we have here is decomposition of anti-canonical divisor class and this decomposition corresponds to geometry, because each of these summons here is the equivalence class of some -2 curve that we got. Okay? So I know I've been talking a lot and probably a bit fast. So, let me slow down and try to make the main point clear. When you construct a space of initial conditions, you need to add the infinities to allow for poles. When you add infinities, you get points where some trajectories can merge. You separate them using blow-up. You create a complicated algebraic surface, and that's the encoding of the surface that you created. Okay? So this surface is known as E61 surface. Okay? And from this surface, you can rid of symmetry. How do you rid of symmetry? Well, so this is what we have. We have a time t here, okay? We also have actually a parameter space here. So my parameters are alpha, beta, or kappa naught, theta, infinity, or whatever. So here you have this surface X that we created. Okay, and in the surface X, you have this configuration of -2 curves, and you have peak of X. So you get the surface X as a blow-up at 8 points of P1 cross P1. Here you have your peak. Okay, and in this peak, you have anti-canonical divisor class, and there is a special condition that this is a unique anti-canonical divisor class of canonical type that I don't want to explain, but I'll just say that this is a generalized Halpern surface, and that amounts to what I just said, unique anti-canonical anti-canonical class of canonical type. You can look at the orthogonal complement here, and this is a sublattice, and this sublattice has this sublattice of span of alpha i's, or delta i's. So this were my delta i's over here, and there's another sublattice span of alpha j, and this is my surface. Okay? So this is the configuration of points that we had to blow up, resulting in the configuration of curves. Alpha i's here, this is my symmetry. Okay? And what is symmetry? Why do I call it symmetry? First of all, what are alphas? Alphas are generated by the condition that alpha j dot delta I is equal to 0. So these are vectors that are perpendicular to the delta vectors in the Picard lattice. You can compute what these alphas are, and they are HF plus HG minus E5 minus E6 minus E7 minus E8. Alpha 1 is HF minus E3 minus E4. Alpha 2 is HG minus E1 minus E2. Okay? They also form a Dynkin diagram. This time, this is a Dynkin diagram of type A21. And this is your symmetry group. So you get the symmetry group by just doing very elementary geometry. And this symmetry group, the reason I call it symmetry is, first of all, it's an abstract affine Weyl group that has the realization using generators and relations. So you have generators W0, W2 for each of the nodes with the condition that each generator is an involution, and in this case they satisfy the braid relation. That's because all of them are connected. In fact, the braid relation is for connected nodes I and j, and if they're disconnected, then the corresponding generators commute. So that's an abstract group, and you can visualize this abstract group by doing the following picture. Take an equilateral triangle like this, and look at the symmetry group of this equilateral triangle. It is generated by reflections. You can see that my triangle is not very equilateral, but all right. So this is the usual dihedral group D3. Then what you can do is, you can sort of now forget about the triangle and do parallel shift of your vectors. You do parallel shifts of your vectors, or of your lines, and you get a kaleidoscope. You get a regular triangular lattice that is like a kaleidoscope. Then each of these wi's, you can choose like one point, and you can think about this as being W2, W1, W0, I think. So, and then by shifting the mirrors, you create this infinite group. And this infinite group, for example, if you start with this triangle, you flip it over here, you flip it over here, flip, flip, you get a translation. Translation is discrete Painlevé. Right, so each element of this group induces a Backlünd transformation, and their particular compositions give you translational dynamics over here, which, when written in coordinates on your surface, gives you discrete Painlevé. Okay, so how do you get these elements? It's probably one thing that I have time to do before we need to stop for the break. It's the following. You have a representation. You have a representation of this A to 1 on peak of x. Well, if you want it to be a vector space, you can tensor over z to q. So, and the way you do it is your wi is a reflection in the root alpha I. Okay? So a reflection here is the usual formula. A class C goes into C minus twice C dot alpha I dot alpha I, alpha I. But because this is minus 2, this is my root condition, you do this. Okay? In particular, exercise, I don't know if I'm allowed to give exercises since this is not a lecture course but a talk. You can compute that W1 keeps F and sends G to G minus K naught over F. And that's an example of a symmetry of your Painlevé equation. It's a Backlünd transformation, but it goes in this direction. You don't fix the surface anymore. You move in the family of surfaces. So you have Painlevé evolution here. You have the symmetry that takes a solution of your Painlevé equation to a solution of a different Painlevé equation for these different values of parameters. And then if you iterate that, you get a discrete Painlevé equation here that you can, by doing a limiting procedure, to get to another Painlevé equation. And we did this full circle. And I still have about half the talk that I was planning to give, but I think it's time to stop and go for a break. I'll stop here. Thank you. Right? Well, if you want, we have 3 translations, but they're all conjugate. It's actually, it's an interesting question, because there is something known as Sakai classification of discrete Painlevé equations, which is sort of classifying all possible geometries. But for each fixed geometry, which is a configuration space, you have infinitely many different dynamics. And then the question is about which dynamics are equivalent, which are not, both on the level of Picard lattice, like are the corresponding directions conjugate or not, and on the level of actual trajectories or orbits on the spaces, but that's a separate story, a little bit more complicated, so maybe some other time, some other day, some other place. Not here, not now. Yeah.
Any further comments or questions?
Yeah.
So you have those singularities, and you remove them, the singularity. How are these singularity points from? From the Hamiltonian structure?
What?
You have that singularity point there.
Mm.
You remove them, and you make the blow up to use this singularity. How are the how do these singularities from?
How do you
find it from? Yeah.
How do you find it?
Yeah.
You do some computation in coordinates. It's basically you write your equation, and for example, if you have f dot, and somewhere here you have something like g over f, you have 0 over 0 singularity. So you basically look at possible.
You use the Hamiltonian formula, or you use
No, it's not in the Hamiltonian formula.
And one more question is about the transformation. You said the transformation is discrete Painlevé-Is. Is this discrete Painlevé related to that continuous ones?
Yeah.
But just
as I said, if you start with some continuous Painlevé and sort of make a circle, this discrete Painlevé has a continuous limit to a different continuous Painlevé. It's related to that cascade that I was drawing before.
Is the transformation unique? Is the transformation unique?
I'm not sure which transformation you're talking about, but let me say no.
Yeah.
No. I'm sure that whatever transformation you're talking about, no is the correct answer. I think Nikita had a question.
Okay, there's further question. Can I need to move out here a bit. Thank you. Yeah.
I don't know where to start. So if I look at Painlevé-6, and I think about the phase, so it's a Hamiltonian system. So it's phase space.
Well, it's a non-autonomous Hamiltonian.
It's not an autonomous system, but it has a phase space which has to do with the sphere with 4 punctures, with 4 punctures and representations of SO2, fundamental group with SO2, and so it has it is actually a D4 type.
Yes.
So how does it become in this family? Where this is to E?
So
structure?
So the parameters when you say we have, so you
4
have
parameters.
Right, but you have rank 2 bundle, right?
Yes.
So if you're looking at Painlevé-6, you can get it as isomonodromic deformation of a Fuchsian system with 4 singular points. You normalize 4 points to be 0, 1, and infinity. You have 1 point left. This is your time. But then for each point, you have to specify its spectral type. Okay? So you have to specify what kind of eigenvalues you have there.
These are your parameters, alpha, beta, gamma, whatever.
So, right, well, once you specify the spectral type, you can sort of gauge, transform the spectral type so that you have like some thetas living at these points, and these are your parameters. Right. So your Backlünd transformations are like discrete Schlesinger transformations adjusting these spectral parameters. So that's this kind of motion, if that was your question.
My question was, where does the E type, the E structure comes from?
Which E structure?
So you have intersections. I thought the intersections of your 2 cycles. It was an E6. It was an E6.
This So right. So if you do Painlevé-6.
So for generic T.
No, wait. Yeah. So if you do Painlevé-6, Nikit, let me show you the picture. I'm in no condition to draw the picture here and without messing it up, but I have the picture here that I can just show you. It may be easier that way. I'm sorry. Unless everyone will want to see the picture, I'll draw the picture. Yeah. Okay, sure. What? Yep. No. I don't remember where the picture is.
Sorry. Can I ask? I have a question to Anton, maybe Kolya too. So this is to
Kolya.
so which one is so if I have a classical mechanical system, it can be non-linear system, with a quantum mechanical system, Anton function is a linear thing, but as the space of function gets bigger, then of course this kind of classical quantum linear system contains the classical nonlinear system. Now at this picture, so here Kolya writes Q Knizhnik Zamolodchikov and so forth that are linear equations that have to do this kind of things act by linear transformations, but in some arbitrarily large spaces. And Anton writes these things acting by rational transformation on some surfaces. Is there some relation between? Is there some kind of relation between one and the other?
I can answer. Now I can answer. So these are your shift operators. So these translations, these Okamoto translations, these are shift operators acting on solutions of the ordinary KZ equation. This is not QKZ, it's before QKZ. Because they change the parameters, these monodromy parameters by some discrete shifts.
But this, in the end, they act non-linearly.
Well,
This is a classical limit.
Yes, what I'm trying to say is there's a classical limit in this sort of linear equation that gets.
The quantization of Painlevé is BPZ or KZ, depending how you look at it. I mean, the monodromy part quantized to KZ, as shown by Professor H.Sakai a long time ago. and the Painlevé is quantized to BPZ, as was shown by BPZ. And this
Okay.
estimations are
Thank you.
Just this is algebra. This is non-trivial algebra. There are Markov surface, Hirzebruch surface with many similar surfaces. Can you comment on it? Do we have something beyond Painlevé, but still with the action of affine Weyl group? Do we have something?
So in general, if you study various moduli spaces of shifts, there's similar kind of Hecke modification. So if you study the Hecke modification moduli spaces of shifts, then you get a many very high dimensional algebra. Moduli of shifts on surfaces. Then you get Then the Hecke modification moduli of shifts on surfaces. They in general some kind of birational transformation that generate this sort of thing. Yes, all of these equations will be beyond Painlevé-II.
well, continuous, no. Discrete, yes. Discrete goes all the way to E8. But I think what happens is if you look at the minimal model like P1 cross P1, if you start adding more points, you lose integrability and you lose affine. So affine is sitting just here.
You can get arbitrary. You can somehow goes arbitrarily high.
Well,
It's just if you want your modular of shifts to be two-dimensional, then you constrain. If you want the modular of shifts to be arbitrary dimensional, then you can get anything you want.
Right. I think Vanya was asking about like the very direct generalization, just staying within that framework, and I think. Yeah. Well, okay. This is a fun topic that you can talk about for like a couple semesters. I like it because I think, to me, this whole thing is very similar to algebra geometric solutions of solitons, where you have nonlinear equation and you linearize it on the Jacobian, and then you pull out solutions. And here you have a nonlinear discrete equation that you linearize by translations on PIC and pull it back for birational representation. I think it's very beautiful mathematics. And we're working on applying it constructively to solve various questions. So, yeah.
PIC is kind of infinite. Can you curve it into elliptic curve or something?
Tea break, coffee. As an organizer, I invite everyone for a coffee break and discussions during the coffee break.
Let's thank Anton again.